Good morning to everybody. It's a pleasure to be there, and thanks for the organizer to give me the opportunity to speak on stochastic master equation. So this free lecture, the goal, in fact, so here you have some of a slide but the goal, in fact, is to understand what's going on, the model of open quantum system, okay, which means that you have a quantum system described by the Schrödinger equation. Everybody knows this. This is rho is the density operator formulation, so the Liouville equation. You have control input, classical input signal, and you have also, through measurement, classical output signal. So what you have is something like this. So if I start here, I think, so you have, as in control engineering, so you have some classical inputs. This is your control, manipulated variables, okay? This is classical signal. And you measure something. This is the output, okay? And of course, for quantum system, so classical signal here, it is typical drive, laser in intensity, frequency, and so on. And measurement, it is classical signal. So we are in the classical world. It corresponds to output of measurement, okay? In the standard description of quantum mechanics. So you have a Schrödinger evolution which describes the impact of U on your system, okay? But you have also the collapse of a wave packet that describe the impact of Y on the system. So you have a first of measurement back action, okay? But it is clear that U and Y are correlated signals, even stochastic. So what are the models between the two? Okay? Of course, you know since Newton's law that you have a correlation between the force and the position. Between the two, you have to integrate second-order differential equation. What replaces second-order differential equation for quantum system? It is called, in physics, stochastic master equation. So I will describe the two first lecture will be on the structure of this stochastic master equation, okay? And they are based on three rules. They mixed the Schrödinger evolution, like this, providing, in fact, unitary evolution of the propagator, okay? You have then the collapse of the wave packet, which means that you take an observable, okay? You take its spectral decomposition, and you assume typically the standard, the usual, the orthodox way. You measure something which gives you on which eigenspace you project your wave function, okay? This is Y, this is this information that you get. And just after the measurement, you have, in fact, the collapse of the wave packet. Here it is written with the wave function, or here it is written typically for the density operator, where Py is just the orthogonal projector on the eigenspace labeled by Y. Okay. And the trick is that you have some information, but it is in the statistic of the measurements. The probability to detect Y depends, in fact, on, the overlap between your system, rho, the density operator, and, in fact, the eigenspace labeled by Y. And this is standard things. And the last point, this is something which is not at all classical things. This is a differential equation. So it is almost, I would say, standard things. This is not standard. And the other point which is not standard is the fact that, in general, you have a composite system. You have your system of interest, and you have a measurement system, the meter. And you have to deal with, in fact, this composite system. And in this case, what you have to use is a tensor product, in fact. So, and to get some information, so first you have to connect your system to your control system, your matter. You have an interaction, which is, in fact, gives you, in fact, the Schrödinger equation, where in fact, you have the free evolution of a system, the free evolution of a matter, and you have an interaction Hamiltonian. Okay? And after that, what you measure is, in fact, something only on the matter. So which means that the measurement operator, O, its spectrum is highly degenerate. Okay. So you have to mix all these things. And if you do this, you obtain typically in continuous time this kind of stochastic master equation. So here you have your drive U, which is, you can say that it is a continuous signal. You have a measurement outcome Y, which is also a continuous signal, but not differentiable. Okay? And you are in the classical world. In between, you have, in fact, rho, the state of your system. Okay? And you have this differential equation with the measurement outcome here depends on a Wiener process, but also, in fact, something that tells you something on where is rho. Okay? So we'll see, in fact, in how we get this equation from these rules in this lecture. And the second kind of system, it corresponds, in fact, to jump stochastic master equation, where, in fact, the detector is a counter. Okay? So the counter is typically given by n here. Where is the counter rate, dn? I don't know. So you have a counter. So you have either, at each time step, either you have no detection, no click, or you have one click. Okay? And you have to update, in fact, the density operator like this. So it is a stochastic master equation, but driven with Poisson noise. And you will see how to get this equation from the three basic rules here. Okay. This is the goal of the two first lecture, and the last lecture will be how to exploit these models for doing some feedback scheme. Okay. But I will spend a lot of time on, in fact, the modeling, because it is a key issue, in fact. Okay. So to do this, maybe I can show something. We will use the photon box, which is a system that has been developed by Serge Haroche in Paris. So maybe I have a small animation. Yes, I have it. So you see, so it is a purely discrete time system. So what you have is the simplest composite system that you can imagine with two key quantum systems. The harmonic oscillator, it is here. It corresponds to a mode, in fact, inside this cavity, okay, at a certain frequency, typically microwave frequency. So you have photon trapped between the two mirrors. So it is a harmonic oscillator. And here you have some, in fact, this pink torus correspond to what is known as Rydberg atoms, okay? And you can model them as two-level system. So it is a composite system made of, I will say, a spring and a spin, okay? Outside the box, so it is a periodic system. So it is a sampling time is around 100 microseconds, okay, no more. And outside this box, you have a preparation of the atoms, typically in ground state, okay? And you send an atom in ground state. Here you have a first manipulation of the atoms, okay, by a first pulse. So you are typically a Rabi pulse, okay, here. Here you have typically an interaction between, in fact, the atoms, in fact, and the photon in this area during the passage between between the two mirrors. Here you have a post-manipulation of atoms, these local things, and here it is the detector. So all the evolution, when the atom gets outside the box, just before the detection, is in a certain sense, in a good approximation, described by a Schrödinger evolution. And then, as soon you assume that the detection is instantaneous, and then you get a signal, which is a signal which is either ground state or excited state, -1 or +1. Okay, here you have a classical computer, okay? You do something, and here what you do some feedback, okay? By proposing here, by sending to the photon a certain, what is called a coherent pulse, with a certain amplitude and a certain phase. And you have a goal in your control, okay? So I will detail most of the time, in fact, the relation between these things, okay? And a little bit the feedback scheme. So, yeah.
So earlier you said that the input is classical. There was a classical input.
The input is classical here. This is your control input. It is what you measure, control input. You have also other control input that could be, in fact, which pulse you put here and which pulse you put here.
Okay.
And there are also control inputs, which is, in fact, what kind of interaction you have. You can, in fact, tune between the atoms and the mirrors and the photon. Okay, typically, either you are dispersive interaction or resonant interaction. So you have a lot of, in fact, here, it is just, in fact, parameter that you can choose. But we are always classical things. It is what it is, some information, classical information that you impose of a system. It is a control inputs in control engineering. And Y is the measurement outcome. So it is, Y is there only. Okay. So everything is here. I will detail the computation because it is not so simple. So you have B is the preparation box. R1 is the first Ramsey, in fact, zone. C, in fact, is the corresponding to the trap photon. R2 is the second Ramsey zone, and D is the detector. So we assume that, in fact, the interaction between the photon and the atoms here is given by this dispersive Hamiltonian. It is typically the tensor product of the energy of the two-level system, ground state, excited state, and in fact, the number of photons. Okay? So, which means that, in fact, you can compute in this setting the propagator very easily. The propagator, okay, it corresponds to this, in fact, unitary evolution. If you are in the ground state, you impose a phase theta on the photon. And if you are in the excited state, you oppose the opposite phase. Okay? And in the, so this is the dispersive interaction. So it is typically, so you can choose here. And you can choose, it is practically, it is chosen by a Stark effect. So we impose, in fact, a constant electrical field between the two mirrors. And you can shift this way, in fact, the energy of a half-spin system, okay, by just a Stark effect. Okay, this. So you can also have some resonant interaction. It is something which is well known. It is come from Jane Scumming. So it is this interaction Hamiltonian, okay, where in fact you catch one photon inside the, in fact, between the mirror, and you get from E to G. So you desexcitation of the two-spin system gives you, you depose one photon in the cavity, and you, of course, you have the opposite, in fact, process to preserve energy. In this case, once again, you can compute exactly the propagator, okay? It is the trick. So let's look at this thing here to see what's going on when we do this. So here is it corresponds to photon measured by dispersive qubit. It corresponds, in fact, to what is called the quantum non-demolition of photon. Everything is here. I will detail a little bit the computation. So you see, this is the propagator between here and just before the detector, okay? This propagator is a composition of three propagators. Here you have the manipulation of the atoms before entering in the cavity. So you see, it's just a rotation, in fact, of pi/4 in different direction here. So you don't touch the photon, you just change G by G plus E over square root of 2 and E by minus G, so you make this rotation. It's something very easily. You are in display. Then you use the propagator corresponding, in fact, to the two photons, to the interaction between the photon and the atoms. So it is this thing. And then you can, since, in fact, after the passage of the atoms in the cavity, you have separation in space, you can still manipulate, okay, the degree of freedom corresponding, in fact, to, I will say, the atoms. And here, in this case, you do a slightly different rotation. Here becomes G plus E, and G becomes G minus E, something like this. Okay, this is the propagator. So you see, it is just a Schrödinger evolution, but on the composite system. And you assume, of course, that outside the box, when the atoms get outside the box, of course, it has nothing to do with the photon inside trapped between the two mirrors. So you have a completely separable state. So the photon, the atom is in ground state, and you have a wave function of the photon. And you applied this propagator on G times C. So what you have? You applies on G tensor psi. First, with this, I have to apply this guy on this thing here, which means that it gives first step, what I obtain, it is, I have me two blocks. This is corresponding to what's going on in R2, what's going on in C, okay? And here what I have, it is just G plus E over the square root of 2 tensor psi. So the system is still separable, of course. And then it is through this thing that you get some entanglement. Just after the passage into the cavity, your system, what it is. If you are in G, you applied exponential of minus E theta n, so it is G over the square root of 2, and here you take the tensor product over exponential of minus E theta n, okay, and I apply this on psi. And if I am in E, I turn in the reverse way. Okay, so it is E over the square root of 2 tensor exponential of minus e theta n plus e theta n psi. Okay? And then I applied this guy corresponding to this, okay, on this. So I just manipulate this. So to do this, I just replace G by G minus E over square root of 2. And here I have just to replace E by G plus E over square root of 2. I'm sure that you understand why the Dirac notation are so important here. To do computation on tensor product, don't use matrices. Use typically Dirac notation. Okay? You see much more what's going on in this. Okay. So if you summarize this, what you obtain is what? What you obtain is something like this at the end. So I will continue here. I obtain if I gather. After that, if I gather G on one side and E on the other side, and I look at what's going on phi on the wave function, I obtain G tensor the cosine of theta n psi plus E tensor E sine of theta n psi. It's just another writing of my state. Okay. And now look here. What we measure is the energy of a spin. So the measurement operator, in this case, measurement operator, it is O. What it is? It is on the spin, it is EE minus GG tensor identity. Okay? Which means that if I detect G, I only conserve this part, this branch. If I detect E, I only conserve this part, this branch. Which means that if I write down, in fact, what's going on in a stochastic way, with the probability corresponding to this number, which is in fact the overlap of psi on the eigenspace spanned by G, okay? I have this, and if I detect E, I have this. And this is the collapse of the wave packet. More precisely, what I have, it is this. So I have the big psi, big one, okay, the big one. What it becomes if I detect Y is equal to G. It is this. It is GG tensor cosine of theta n psi over the square root of psi cosine square of theta n and psi. Okay. Or if I have the other one, it is EE tensor minus E plus E sine of n theta on psi, and I divide by the norm of this guy. It is the square root of psi sine square of n theta psi. If I detect Y is equal to E. So what is important, just after the detection, the system becomes separable. And what's going on with the atoms? The atoms crash on the wall of the cryostar. You don't care about the atoms. Okay? So what interests you, it is just this part. And then you send a second atoms that passed, and so on and so on. Okay? But you throw away the atoms in this case. And physically, they crash on the wall of a cryostar. Okay. Yeah?
Thanks. So in the first slide, you said the spectrum of the observable O is highly degenerate.
Yes.
Or something. Is it true for this?
Yes, of course, because the spectrum, so what are the eigenvalue of O? What are the eigenvalue of this guy?
And minus 1.
It is, I have +1, and what is the eigenspace?
E.
It is E, the eigenspace, tensor, the full eigenspace on the cavity.
Okay.
It is an infinite dimensional.
Yes. Yeah.
And if it is -1, it is G, tensor,
The full.
this thing.
Okay.
So it is highly degenerate.
Thanks.
Okay? Yes, do not hesitate to ask questions. Yes.
So, since at every round you're sending the Rydberg atom always in the ground state,
Yes.
I'm not sure exactly how the next round will depend on the previous round. I'm not sure I understood that.
What do you mean?
So you're saying you have a Markov process, right?
Yes, the Markov process is this. So if you want to simulate what's going on, assume that you can do on your computer if you want. It is very simple. You start at step 0 by a certain value of psi. Say, I don't say typically a coherent state. And then you take, I send one atom, and then I measure. To do the measurement, just, in fact, applied this rule, but in a Monte Carlo simulation, which means that you draw a random number, okay, between 0 and 1 with your favorite random number generator. And if this random number is greater than this one, you choose this, okay? Or if it is less, you choose this. And you choose this branch. This gives you a new psi 1. And this new psi 1, then you send another atom, which is 2. This gives you another outcome, and so on. It is what is called quantum Monte Carlo simulation trajectory. Okay, it is very easy. So, and typically, if you want, yes, I have a MATLAB program to do that. It is so simple to do this. I guess I have it here. Yes, it is here. So this is the ideal model. So you see, it is something that you can directly use. I use MATLAB because I am a dinosaur in programmation. Now you use Julia or some much more elaborated language. So here you see, I define the operator. Here I define, in fact, I choose a little bit because I can also assume the dephasing per photon and the phase here. I choose the number of atoms that I will send. And I start typically from identity, okay? Of course, I truncated to maximum of 7 photons, okay? And then I do this loop. So you cannot imagine something simpler. Everything is here. So it is the density for, operator formulation, okay? So you have to sandwich. So you have your two measurement operator, or cross operator, mg and me. It is a cosine and sine. Okay? You have your two branch corresponding to this thing, but in the density operator. So here it is just for graphics. If my random number is less than the trace of rho g, which is exactly this thing, then I choose -1. and I update to rho g. If it is greater than this one, I use this one, and then I normalize. And let's try to see what's going on if you iterate, typically. You have this thing. Yeah.
The quantity n there is the number of photons in the cavity, or like
So
sine n theta you're using?
what I assume here, okay, is that initially in this simulation, okay, I use a completely mixed state.
Okay.
Identity. I do not have any idea. I know that I have between 0 and 7 photons, but I have no idea of the number of photons. So I use a completely mixed state. And then I measure.
And in these formulae, when we are saying this sine n theta, cos n theta, so
Yes, it is there. Sine, it is M, it is a diagonal matrix in the Fox basis. I am in the Fox basis. It is this diagonal, and here I present the computation with only theta, but you can also, just by choosing, in fact, the phase of your second Ramsey pulse of pi/2, you can put a phase here, okay? Just the computation are a little bit more involved, but it is the same, okay? So you can put any cosine of, here it is typically the dephasing per photon. Here you have the number, the photon number, and so on. So it is nothing this. So it's, you cannot imagine simpler things. We can, so I take this initial state, and it is interesting to see what's going on at the end. So you see, yes. It hasn't converged, but you see, we start, you see the collapse of the wave packet. Here. You are here, and after a certain time, we oscillate between 1 and 2. And then it starts to do something like this, and it seems that the convergence could be some, on typical trajectory, convergence could be quite long, in fact. Let's do another one. It is a stochastic process. It is another realization of a stochastic process. In this case, it has converged to a pure state corresponding to 2 photons exactly. Okay, and you continue. You do, it is as if you do the experiment. It is much easier on your laptop than in the real world, of course. And it is a perfect in the perfect case. And you do this a lot of time. Okay, you do this a lot of time. And what can you do? After that, you do the statistics. How many times I converge to 7, I converge to 0, and so on. Okay, it is exactly this. And you see, you can infer what's going on by the statistics of the click. At the end, you see these blue regions. I guess that it is 7 or 0. I don't know exactly. But it is almost all the atoms are get outside in G. Okay, if I converge to another point, it is the same here. Here. In this case, it depends, in fact, on the statistic of G and E. And the information is in the statistics, of course. And at the end, if you neglect this part, it is as if you have a projective measurement on the number operator. Okay? And you choose, in fact, you detect on which number you are just by looking at the statistic corresponding to the statistic of this thing. Okay? So what you have is with this thing, I will go back. It is this. So I have this density operator here. I have this measurement operator. And for, in fact, theta over pi irrational, in fact, what you can prove is this. So you have, it is, this thing is correspond to what is called the super martingale, okay? And to discuss a little bit what is a martingale or super martingale, for people who are not familiar with a stochastic system. So you know that it is a Newton invented differential equation. Differential equation, you have constant of motion, first integral, okay? And for stochastic system, you have something which is not deterministic, but you have something which is conserved in average. So which replace first integral is martingale in this case. But also what you have on system, typically mechanical system with friction, typically, for example, a pendulum like this, I assume that there is some friction in the air or, in fact, friction on the rotation axis. You know that after a certain time, I reach the stable equilibrium. So I converge always to this. In this case, in fact, the energy, which is conserved for the perfect system with friction, it decreases. So which it is called in dynamical system theory, Lyapunov function. For stochastic system, you can imagine exactly the same thing. Something that in average decrease. So if you have something that in average decrease, which is V in this case, okay, which is positive. And if you prove that it decreases to 0, you know that at the end, you have something which in average decreases to 0, which is positive. You know that at the end, it is 0. You have to look at what are the rows such that V is equal to 0. And on this thing, the row where V is equal to 0 corresponds exactly to a Fock state. Okay? Because rho, it is a density operator, so it's diagonal, okay, corresponding to the population, okay? And what you do with V, just you pick up the product of two different, in fact, diagonal elements. And you assume that all this product is 0. And since the sum of this element is 1, the only possibility is only one is not 0, and the other one are 0. Since the trace is 1, which means that you have only one solution which corresponds to a Fock state. So how to get this formula? So it is how to get typically first integral in differential equation. There is no general method for that. You have to guess that. Okay, this thing. And here exactly, so it was an idea of Maziar Meraimi and Alain Sarlet to use this function. And if you compute the expectation value of this function knowing rho k with this thing, you obtain exactly this formula. It is less than this. Okay, I'm not sure that I have time to do this. Maybe I will, since I have a lot of things to do. It is a very good exercise to compute this. So what is this? You know what it is. I just start the initial thing. What is the expectation value of V of rho k plus 1, knowing rho k? It is the probability that y is equal to g knowing rho k, okay? And then I have to compute V, but with rho k plus 1 corresponding to g. So it is mg rho k mg dag over the trace plus the probability that y is equal to e of rho k and yk, excuse me. And here I take the value of v when I take me rho k, me dag over the trace. Okay, you normalize always. And you do the computation, okay? And you can have this, in fact, upper bound. And this upper bound tells you what if all these numbers, also this cosine, are different of 1 in absolute value, okay? Then you have something which, in fact, strictly decreases. Okay? Since when you iterate, this means that for the expectation value of v at a certain time, knowing rho 0, is less than the product of this number times v at 0. Okay? So, and you know that you converge exponentially to 0. So it is robust. If you perturb it, you still have this exponential convergence. Okay? In this case. And the last point is that, so you know that you converge to a Fock state. Okay? Almost sure convergence, but in practice, you always converge. Yes?
Sorry, it's not obvious to me why the fact that a functional of the state converges guarantees that the state converges. Like, is it enough?
No, it is not enough. You have to use the fact that V, look, V, in fact, converge to this, okay, and you have exponential. So what you have to look at this, it's what is called, in a certain sense, an invariance principle. You converge, of course, at the end, you see, you take a long trajectory, at the end, V is 0. You agree? But you have also to respect this rule. And if you mix both, corresponding what is called in classical dynamical system theory to Lassalle invariance principle, the only possibility is a Fock state. Okay? It is this. And the last point, which is important, is this. Because on this system, you have a lot of first integral, a lot of Martingales. And the Martingale, so if you take any function of n, this operator, it is constant in average. Which means that if I take the expectation value of the trace of f of n, rho k plus 1, knowing rho k, it is exactly the trace of f of n rho k for all f function of n of n. Why is it like this? It is obvious, in fact. Use this formula, but with v is equal to f of n, the trace of f on n rho, okay, the trace. And in this case, it is linear. So this probability is exactly this one. So it's cancelled, okay? And what you have to look at is this. This is equal to the trace of what it is. It is f of n, and I have mg rho mg dag plus me rho me dag. Okay? But all the operator commutes. Okay? So because mg is a function of n, me is a function of n, so I can put the rho on one side and all the operator on the other side. And I know that mg square plus me square, which is sin square plus cos square, is 1. So I recover the trace of fn and rho. Okay? So you have a lot of Martingale. And because of this, you deduce very easily. So you know that, in fact, from this Lyapunov function, okay, you converge to a Fock state. And now you see what are the statistics of a convergent point. For the statistic, you have to preserve this. So which means that the trace of expectation value of a trace of rho k and any function of n is equal to is constant. The only possibility is that the probability to converge to state n is exactly the initial population. Okay? So with this mechanism, you have completely analyzed, in fact, the stochastic behavior of your system. And it corresponds exactly to quantum non-demolition of photon, because you preserve the energy. Okay? Well, yeah?
Martingale was, and what is the connection to Martingale here?
Yes.
So you see a reduction or convergence, is that what defines?
So the fact that you agree with me that with this Lyapunov function and with this, we have the proof that any realization converges to a pure state.
Yeah.
But when I take several different realizations, of course, I have different value of converged state.
Yes.
And then I want to do the statistics. Okay? If I do 1 million of realization, what is part of a realization converging to 0, to 1, to 2, and so on. But to do the statistic, the best thing to do is to say, well, I know that for any function of n, the trace, the average value of f of n is constant. So if I take typically n, if I take that f of n is typically projector of certain value of n bar. Okay? What I have that the trace of, so I have n bar rho k n bar, its expectation value is equal to n bar rho 0 n bar. You agree?
Yeah.
So if I do this, if I compute this by doing a lot of realization and taking only the row that converge to n bar, I know that I should recover this number.
Yes.
So I know that when I start my measurement, the probability to detect n bar is exactly the initial population on n bar.
Yes. I think what I didn't understand is what is a martingale?
A martingale is something which is preserved in average, which means that, yes, the definition of a martingale. It is something like this. Okay, martingale is this. So here, a martingale okay, it is something, so typically we have a state here. So it will be, I will say, W of rho. Okay, it's a function of a state. Rho is a stochastic variables obeying to this. And a martingale is by definition, it is something with the expectation of W of rho k plus 1. Knowing rho k, you can take this is equal to W of rho k. Just this, the definition. It is constant, but in average, because you have a stochastic system.
Okay.
It is typically the analog of first integral for dynamical system.
Okay.
Something which is invariant, but it is invariant in average for the dynamics.
Thanks.
Okay. Well, if you, okay. If you can do, I will not detail this, you can do exactly similar computation, but with, in fact, resonant interaction. In this case, if you do resonant interaction, it is the way if you want to prepare the cavity in an empty state, in vacuum. You send an atom in G. You assume, in fact, you do not manipulate it. You take it, just this. So you do nothing here. You prepare it in G. Do nothing here. Do nothing here. Okay? And even you do not need to, in fact, to measure it. Since you get in G, since it is in resonant interaction with a photon. If you have some photon inside the cavity, from time to time, the atom will catch one photon. Okay? And the cavity will have one photon less. At the end, you obtain 0 photon. It is some, you remove all photons from a cavity. So so it is more or less for physicists, it is more or less obvious. Okay, this thing. But if you want to check that from a mathematical point of view, your model, you have this. So this is in fact the propagator. If you apply this propagator on G, okay, the initial state is G. You only have to take this part, G, this one is 0, and this one. So what you obtain is this. You obtain a sum of two things, G tensor, a function of n on psi, plus E, and here you have something which is a function of f, but here you destroy one photon. And now if you look at your system here, your system is governed in this case by this rule, and it is very easy to prove in this case that if you take n and you take the expectation value of a trace of n rho k plus 1, it is less or equal to the trace of n rho k. And you have some additional condition on this. So of course, to have always non-zero here, you need that this number should be never, the sign of this number should be never 0. Because in this case, for typically what is called trapping state, you never have this for a certain number of photons. So if you have plus a condition, okay? And this is what it is. It is a super martingale. And if you typically, if for all n, the sign of theta, the square root of n, okay, absolute value is strictly positive, then you know that you always converge to the ground state. Okay. Well, so I will not detail this more. So this is this formula, you have this thing. So you have the expectation value of this thing, it is this, minus this guy, and this guy, if it is never 0, it is you decrease, every time you decrease always with something. And if this operator is not 0, okay, at the end, you decrease to 0, okay? It is something a little bit different. Well, if it is not, if you have some rational number, it corresponds to what is called in micromaser and so on, which is called trapping state. So it is, so if from time to time you have 0 here, you have, look at the point where you have 0, okay? You have something where you have some invariant zone. If you have less than this number, you can only decrease, which means that if you are less than n photon, you always are less than 1 photon. Okay, so you have a lot of, so you have this invariant space. You have a lot of invariant space. in this case. In this case, if you take H n bar correspond to a span of 0 until n bar, donc, and if the trace of rho k of rho 0 and if you take the support of rho 0, it is included in Hn bar, then for all k, rho k is included also in Hn bar. This comes from this. If you are inside n bar, it doesn't change. You cannot increase one photon, and here you destroy one photon, get one thing. Okay? And when this guy is 0, you can decrease, but until the first 0 that you encounter. If you are just behind this 0, you can still decrease, and so on. So you have some trapping zone, like this. So you have something like this. If I draw here a scale, 0, and here I have the first value where the sign of theta square root of n bar 1 is 0. Here you have the second one. The square of n bar 2 is 0. If you are here, you decrease to 0. If you are here, you decrease to there, and so on. Okay? It is typically the behavior of this stochastic thing. Okay? But what I presented is something where the measurements are perfect. But in practice, nothing is perfect. I'm not perfect, of course, but the experiment is not perfect. So, what's going on, typically? Imagine that your detector is broken. This is the worst imperfection that you can imagine on your detector. You have to do something, because you have sent an atoms, and it has to interact with a photon. It is as if you should have a measure, but the measure is not given to you. So you do not have this information, because your detector, this stupid detector, it doesn't work. So the only things that you can do is to compute the expectation value of rho k plus 1 knowing rho k. And in this case, what you obtain, what is called in information, quantum information, is a quantum channel. So you see the relation between measurement, quantum channel, and so on. But assume that your detector is not completely broken. Assume that you have some detection errors. And it was typically what's going on in the experiment. It was 10% of the time, the detector tells you G, but the true collapse was in E. You have you have some information. So what is the update in this case? Okay. And here, what you do, it is the minimal interpretation of the rules of Copenhagen rules is Bayesian point of view. So rho summarize in a certain sense the information you have on your system. If you get new information, you have to change your probability law, because rho is just a probability law. Okay? Quantum 1, but it is a probability law. So you have to change your probability law depending on the information you get. It's like in the, I will say in the Monte Python, what is Monte Hall game, you know, with 3 doors and so on. So with this famous TV game, okay? It is typically Bayes. So what you have these things. Detection error. So I will take the case, you have many, But what I have, I assume that I know my error rate. So I know that I detect y is equal to E when the atoms collapse in G. Okay? I say that it is eta G. It is something which is between 0 and 1. And I have this, the second one, because the error could not be symmetric. It is when I detect y is equal to G, knowing that the atom is equal to E. And I put that it has eta E. Okay? And now what I will do is just, I will use this. Okay? But I will use this, but I have to put something, a weight here and a weight here, of course. Because I have to do something like this, I get some information. So the way to update your quantum state is to use this. Of course, everything is conditional. So this probability here, okay, are classical probability. Okay, they do not depend on rho k. But in my computation, since I block rho k, I will not, in fact, always assume that the probability depends on rho k. I just want to have the reverse one. Okay, here. Because I want to have what is the probability that the atom is in G, knowing that I have detected Y in E. And what is the probability that the atom is in E, knowing that I have detected E? Okay, I need this, typically. So assume that, assumption, do this. I assume that Yk, I get Yk is equal to G. And use typically the Bayes rule. Okay, what I will say that, what is rho k plus 1? What k plus 1 is the probability that the atom is in G, knowing that Yk is in G, and rho k, of course. If I have this probability, I have to take mg rho k mg dag over the trace. Plus the probability that the atom is in E, knowing that I have detected G, and knowing rho k, and here I have ME, rho k, ME dag over the trace. And what I have to do is I have to, so rho k is always in the conditional probability, okay? What I have to do is to reverse these two. And to reverse these two, all what you have to do is to use Bayes rule, which means that if I do the computation here, remember this thing. So I use my favorite Bayes rule. So I have a probability. I am interested by this. Atom is in G, knowing Y is in G, times the probability that Y is in G. No, yes. What it is? It is the probability that Y is in G, knowing that the atom is in G. Of course, you are okay, and times the probability that the atom is in G. Okay? You agree? And I have exactly, I know that I block this, so I have a probability that the atom is in E, knowing that Y is in G, times the probability that Y is in G, is equal to the probability that Y is in G, knowing that the atom is in E, times the probability that the atom is in E. Okay? And I know, something here. What I know is this. This, it is just I know that Y is in G, okay? Atom is in E. Yes, atom is in G, so I condition Y is in E, so this guy is 1 minus eta G. You agree? It's the complementary of this guy. Because the probability of atom is in G, Y is in G, atom in G, plus Y is in E, atom in G is 1. So I know this guy. This, I know. It is what it is. It is the trace of mg rho mg dag. Here, it is exactly what it is this. It is eta E. Okay? And here, it is what it is. It is the trace of me rho me dag. And here I know that these two guys is, the sum is 1. So if I take the sum, I obtain the probability that Y is in G, knowing OK. And then I can compute this, okay, without any problem. And the fact that, you see, when atom is in G, knowing what's this, it is always multiplied by this guy. So it simplifies here. It is something stupid here. It simplifies here. Simplifies here, and what you obtain is these rules at the end. Which means that the probability, so okay, you have this update. And the trace, the normalization, is exactly the probability to detect Y. And you can look at this formula, for example, if I assume that eta G is 0 and eta E is 0, I recover, okay, the previous things. And now, if I assume now that eta G is 1/2 and eta E is 1/2, it is as if my detector is broken. Because I have exactly the same formula here and here, I divide by 1/2, so it is exactly, so detector broken is 1/2 in any case. Okay? And here you have this thing. Okay. So what we have is, in fact, this Bayes rule. You can imagine something. So you have this in the, yes, if you look at my web page, so you will find me, you take Google Pierre Rouchon, you will find my personal web page. You will have some lecture note explaining this, okay, all these things, okay. So you have a lecture note, and I will put after the last lecture also the slide, okay, on this, and you will have also the small MATLAB simulation, okay, things. So now you can simulate, and I will show you this. On MATLAB script, in fact, this kind of things. Okay, it is exactly simulation. Yes, it is here. In this case, it is detection efficiency. It's a little bit different. Okay, so from time to time, detection is not perfect, okay, and so on. So at the end, you will have all the details in the notes. So you have some mixing like this. Okay, it is this. So it is typically what's going on the detector. So you do Monte Carlo simulation, okay? And in these things, you have other things like this. You have the fact that the detection efficiency is, I will say, 80%. Okay? But you have another point, is that the preparation box, the atoms getting outside the preparation box, is not perfect. So how it works, it is you have a thermal, in fact, it is in an oven, a small thermal things with average velocity is 200 meters per second, okay? You open the slot, you cool down the atoms, okay? All this thing, and then the atoms get outside. But when you open, From time to time, you open for the atom slot and you have no atoms. So you have a certain occupation, probability of having an atoms in the atom slot. Okay, and it is typically, I would say 80% or something like this. And the detection efficiency is 80%, so you have to multiply this, because detection efficiency is that the atom has passed, but the detector presents no click. So y is 0. Okay, all these things. So it is exactly what you have. You have here, in the simulation, you have all these parameters corresponding to more or less what was in the experiment. So you have 80% that an atom is sent during the slot. You have, so 1/2, we have 80% that you have detect these atoms. And once you have detect, you have something where, in fact, the detection efficiency, the error is not exactly the same. You have a sort of misbalance corresponding to what is called the Ramsey oscillation. In fact, it's not perfectly centered. And then, of course, since you have all these things, you need much more atoms to get convergence, because the information gets in the statistic much more slowly. But you still have, with this, convergence to, in fact, a Fock state. Okay, and you see in the statistics all these things. But you can also add something more. You can also use the fact that the photon lifetime inside the cavity is not infinite. In this case, it corresponds to this. So I show you the MATLAB code. It is this. So here you have all the things. So you do in this part of all these things. So it corresponds to detection. But at the end, you need, in fact, to say, well, during the passage, during this evolution, I do not have, I have no loss of photon. I have to destroy one photon, or if I am in a thermal environment, I have to inject one photon. So I have another cross map, which is this one, corresponding to, in fact, a thermal environment of a photon, with, in fact, M0, M minus, and M plus corresponding to no photon change, plus one photon, minus one photon. You do this. In fact, it corresponds to a thermal environment. And you can put all this, and at the end, you obtain something like this. So I will show simulation on this. So you see here, I start with a pure state corresponding to, in fact, free. So you see here, it is a coherent state, okay, of free photon, which is very easy to prepare. You start from 0 and you inject with your controller a specific pulse, microwave pulse, classical things, inside the cavity. And you obtain this. This is what you see. And what you see is the progressive collapse. So you see, I start with this, and here I am quite lucky in my simulation. More or less, I reach around 5 photons. But now you have a decoherence process. After a certain time, I reach 4 photons. Then I have 3 here, then I have 2, then I have 1, and then I reach 0. Because it corresponds to the slow decay of a cavity. So you measure, your measurement is quite fast. But when the cavity destroys 1 photon, it doesn't tell you. But you see this through the statistics. You see the statistic change. We see this in the measurement outcome. And you can do typically what is called the most likely photon number, and you obtain something like this. here, where here, you see, here it was a photon coming from the thermal state, trapped inside the cavity, and just after that destroyed. And it was amazing that this kind of experiment has been done in true. The life, the birth, and the death of one photon. It was a wonderful paper, I put it. You can do this with your simulation if you want, but just, okay. So I think I will conclude by this. It is, I guess, that more or less you are convinced that in discrete time, you have this formulation of discrete time stochastic master equation. So I will explain the trick. And you will see that it mixed quantum probability with classical one. Just this. What you have two objects. You have first, I will say, you have a partial cross map with a different outcome. I will say sigma. Okay? And this is a partial cross map. These things, où est-ce que j'ai mis mon truc? The pointer, I don't know where I put it. I lose it. Oh, no, it's there. Maybe it will be easier for me. It is this. You see, it's a partial cross map. So it's not fully mg rho mg dag plus mi rho mg dag, but I put some number here which are less than 1. So I pick up. So I have my quantum channel, and I pick up some term on my quantum channel with coefficient, positive coefficient between 0 and 1. Okay? And it is exactly what I say here. I have k for 1, 1, 1, 2, 1, 3. But at the end, when I consider the sum like this, k of rho is the sum on y of k y rho, I have a quantum channel. A map which is linear, which preserves complete positivity, and the trace. And then I have to mix them through, typically, a stochastic matrix, which is eta. So the number of entry here is the same as this one, but here I have a stochastic matrix. It is eta. Here it is. No, it is not this. It's not here, this thing. It is my, so it is, I will say, mu, what I take here. So I do this. I always, voilà, it is mu here. K mu, mu1, mu2, mu sigma, okay? And son of mu, K mu is this. And here I have a matrix where here I have mu, and here I have y, okay, as dimension. And here I have elements which are eta of y and mu. Alors, these elements are positive, and when I take the sum, it is 1. The sum of each column is 1. Okay? So it is a left stochastic matrix, because the vector 1, 1, 1 it corresponds to the left eigenvector of eigenvalue 1. Okay? And when I do this, I multiply these two things, and I obtain k of y1, k of y, I will say certain number, I will say m, number of measurement rho. So rho, it is a mixture, you see, like this, where the coefficient corresponding to this entry. And in the case which is this one, okay, the eta, what it is? It is 1 minus eta g and eta g, and 1 eta e and 1 minus eta e in this case. Okay. And the last point is that the normalization, so it's exactly the probability. Which means that with this model, you have a probability of detection. So you can do a lot of things with that. You have all the statistics. Even if you, so of course, you need to model the imperfection to model a quantum system. But if you have this physical parameter, or you can do something like this. So you can compute the likelihood function. You can compute typically what is the probability to detect yk, y0, knowing rho 0. It is just the product for L is equal to 0 to k of the trace k minus 1 of the rho k k of yk of rho k, or L. It is this. Or it is, if you prefer, it is this. It is the trace of k of y k composite with yk minus 1 composite of y0 and rho 0. Is exactly this. But for numerical computation, you do not use this formula because this probability shrink very rapidly. Use the log. The log of p of yk, y0, knowing rho 0, put it is lk, and you have lk plus 1 is equal to lk plus the log of the trace of k of yk, okay, k minus 1. In the log. And here, with all these things, you can do what is called a Bayesian estimate or max-like estimate, and so on. You have in a numerical way. Okay. So we have a likelihood function directly with this. Okay. So, and you will see how to use this in particular. Pierre Guillemin will give some how to exploit this kind of stuff, and also Antoine Tilloy when you have bin information, typically. You have a sum, not exactly. You don't have yk, but you have a sum which is corresponding to bin information. Okay, but it is based on these things. The trick is this one. And of course, so we will see next. I think I will stop. Okay, it's time. Seems to me it is 11. Yes.
You have 5 minutes.
Yes, yes. And I will stop. I think it's. And I will do next time. I will do how we go when we go to, in fact, continuous time system. So it is something which is pedagogical here, but I will use in this case qubit measurement with dispersion photon in discrete time. But at each time step, I want to get only a small small kind of information. And I will shrink this information to 0 and take the continuous time limit, okay, in this case. It corresponds here. It's not very difficult to see what we have. It is when here the theta is very small. So at each time step, you get something where, in fact, when, not here, it is not here. When theta is small here, it corresponds to jump. It is there. Here. When theta is small here, it corresponds, in fact, to something. Okay, so you almost do few things. When theta is very small, and you can do a lot of things. Okay, yeah.
Hello. So here in each iteration, this local drives that R1 or R2, that is fixed that you are keeping. But if you still update it based on the outcome,
Yes.
does that give you more freedom and it reaches faster, or?
Can you repeat? I do not
Yeah.
catch.
So these first the G minus E over root 2 that what
Here,
is,
yes.
and this R1 and R2, this local drives that you are giving.
Yes, we can change this drive, of course.
So
we
if
can
you
manipulate this.
Update that based on the outcome, some sort of.
Yes, we can manipulate this based on outcome, of course.
So does that give you faster collapse?
Yes,
or?
yes. You can imagine exactly to do some feedback scheme, depending on the previous measurement.
Yeah.
You change here this thing, okay?
Yeah.
Or theta. It is much more clever to use theta, to change theta, to achieve convergence much faster. But it is feedback scheme. So I will speak this in the last lecture, in lecture 3. So it was okay. Because typically what you have here, it is at each time step, you have one bit of information. So if you manage to get exactly and to write a number, n number of photons, which is you need the log of n bits. And of course, you should converges in log of n number of atoms. Okay? In this case, you can do something like this. Yes, exactly. Precisely. Yes, you can do a lot of things. So here I just present the basic, in fact, models, okay? And then you can enrich all these things. So here I can change. This is here I can put any unitary evolution here. And here also any unitary. And I can also prepare my atom not in G. Take, for example, atom. You can take here, if you take also other imperfection, it's your atom is not exactly in G. You have a small thermal state. You have GG plus something few, a bit of population in EE. In practice, you have to take this into account. Okay, we take this into account. But it is, you can summarize this in eta E and eta G. It is more or less the same. Okay, it is gathered in only this parameter. But you can, and here you can also use some decoherence inside this block and so on. Okay, but it will be small correction to this model. So it is important to understand the pure case, and then you know that more or less your system is close to that. Even at the end, it is not very close to that. But you still have something to understand what's going on, okay, in a perturbative way. Voilà. So no. If you have a question. No problem. So it's nice to have question, in fact. Wednesday at the same hour. And I will do exactly more or less the same thing, but for continuous time system. Voilà. So if you have some question,